What if the universe at its most fundamental level is profoundly indecisive? What if every solid object you've ever touched, every immutable law of physics you've ever learned, is built upon a foundation of pure shimmering uncertainty? You are, sitting in a room on a chair, a solid, dependable object. It supports your weight without question. It has a definite location, a precise boundary between where it is and where it is not. This is your reality, the one your senses confirm every moment of every day. It is a world of substance, of cause and effect, of concrete answers. But this tangible world, this classical certainty that we inhabit, is a grand illusion. It is a spectacular facade constructed from a realm so bizarre, so contrary to our intuition, that its pioneers questioned their own sanity. Peel back the layers of the familiar journey down past the molecule beyond the atom, and you will arrive at the quantum domain. Here, the comfortable rules of our existence dissolve into a mist of probability. Here, in this subatomic wilderness, a single particle can exist in a dizzying multitude of places at once. It is not here nor there, but everywhere at times could times be all at the same time. This is not a metaphor. It is a fundamental property of matter we call superposition. Imagine a single electron, not as a tiny solid marble, but as a ghostly wave of potential, a statistical cloud of existence. This cloud represents all the possible outcomes of its future. It is a symphony of might have beens played simultaneously. Only when something forces the issue, when an observation is made, does this wave of possibility collapse, and the electron reluctantly chooses a single definite location, as if finally making up its mind. For that fleeting moment, it conforms to our classical expectations, but the instant we look away, it dissolves back into its phantom state, its ghostly shroud of probabilities. This isn't just a theoretical curiosity. It is the engine that powers our digital world, from the transistors in your computer to the lasers that read your data. We have harnessed a ghost to build our civilization. We rely on a paradox for our progress, and the strangeness only deepens from there. For in this realm, particles can become entwined in a mysterious conspiracy, a phenomenon Albert Einstein famously derided as spooky action at a distance. We call it entanglement. Imagine two particles born from the same event, forever linked, like cosmic twins. They can be separated by the width of a laboratory bench, or by the gulf of 1 billion light-years. The moment you measure a property of one particle, say its spin, you instantly know the spin of its distant twin. Instantly. Faster than the speed of light. It's as if they are communicating across the vast, silent emptiness of space, sharing a secret that defies our understanding of time and distance. There is no message sent, no signal that travels between them. They are simply two parts of a single, indivisible system, a unified whole that just happens to be stretched across the cosmos. Their fates are bound by an unbreakable thread of quantum information. Our universe, it seems, is not a collection of separate things, but an interconnected, holistic web of profound and unsettling intimacy. So we are faced with two completely different descriptions of the same universe. One, the quantum world, is a realm of fuzzy probabilities, ghostly superpositions, and spooky instantaneous connections. It is a world where nothing is truly certain until it is measured. The other, our classical world, is the reality of our experience. It is a place of solid objects, definite properties, and predictable trajectories. A thrown baseball does not exist in a superposition of all possible paths. It follows one and only one graceful arc. The moon is not in a dozen places in the sky at once. It hangs in a single, predictable location. The chair you are sitting on is resolutely, stubbornly, and thankfully times here times and not also simultaneously across the room. The transition from one world to the other is the greatest, most profound mystery in all of science. It is called the measurement problem, and it is a chasm that has divided physicists for a century. How precisely does the act of looking, of measuring, of observing compel the indecisive quantum world to make a choice? For decades, the answer was shrouded in philosophical debate. Some believed it was the consciousness of the observer itself, the act of a mind comprehending the system that forced reality to snap into focus. This idea, while tantalizing, placed humanity at the center of cosmic importance, a position science has taught us to be wary of. Others proposed even more radical solutions, such as the many worlds interpretation, which suggests that the universe doesn't choose at all. Instead, every possible outcome of a quantum event actually happens, each one branching off into its own parallel universe. In one universe, the electron is here. In another, it is there. In this view, we are adrift on one branch of an infinitely sprawling cosmic tree of possibilities, oblivious to the countless other versions of ourselves living out the lives of might have been. It is a breathtaking, terrifying, and completely untestable idea. These theories and many others all grapple with the same central wound in our understanding, the violent tear in the fabric of reality that separates the quantum and the classical. Where does the quantum world end and our world begin? Is it at the scale of a molecule, a grain of dust, a virus? There is no clear dividing line. There is no known boundary where the rules of the game suddenly change. This is the colossal paradox we are here to explore. The universe should not work this way. It should not be two different things at once. There must be a bridge across the chasm, a mechanism that explains how the solid, predictable world of our experience emerges seamlessly and reliably from the ghostly, uncertain quantum realm. We have been searching for that bridge for 100 years, and now a new and powerful idea is taking hold. It is a theory that doesn't require mystical consciousness or infinite parallel universes. It is a theory grounded in the most powerful explanatory framework ever discovered by science evolution. It's called Quantum Darwinism. The name itself is a revolution. It suggests that the classical reality we perceive isn't something magically imposed upon the quantum world. Instead, it times from it, through a brutal process of natural selection. It implies that the objective stable properties of the objects around us, the position of a planet, the color of a flower, the hardness of a diamond, are the fittest quantum states, the ones that have survived a relentless cosmic contest. The theory proposes that as a quantum system, like an electron, interacts with its surrounding environment, a deluge of air molecules, a flood of photons, a bath of radiation, it effectively leaves copies of itself scattered throughout that environment. Information about its state, its position, its spin, is imprinted on countless other particles. Think of it as a cosmic census. The environment is constantly, relentlessly, and passively observing every quantum system within it. But not all quantum information is created equal. Some states are robust. They can create many copies of themselves in the environment without being destroyed. They are stable, strong, and capable of proliferating their information far and wide. Other states are incredibly fragile. They are destroyed by the slightest interaction, unable to leave a lasting record of their existence. Quantum Darwinism argues that we as observers never actually see the quantum system itself. We can't. We are too large, too clumsy. We only ever see the information that has successfully been copied and broadcast into the wider environment. We are accessing the public record. The stable classical world we perceive is, in this view, a consequence of this cosmic survival of the fittest. The quantum states that are robust enough to imprint themselves onto the environment, thousands, millions, billions of times over, are the ones that become objective reality. They are the fittest states that have been selected for by the universe itself. Their existence is agreed upon by a vast consensus of environmental particles. All the weird, fragile superpositions, the ghostly alternatives, are driven to extinction almost instantly, their information scrambled and lost in the noise of the cosmos before they can ever establish a foothold. What we experience as a collapse of the wave function is not a magical moment of choice. It is the end result of a fierce, hidden competition. It is the victory of the stable and the death of the fragile. Objectivity, then, is not a fundamental property of the universe. It is an emergent one. It is a property that is fought for and won at the quantum level. The universe itself, through a process of Darwinian selection, filters out the quantum weirdness, leaving behind the solid classical reality that we can all agree upon. It is a process of the universe observing itself into existence. This is a profound shift in our understanding of everything. It suggests that reality is a democratic consensus, voted on by the countless particles of the environment. It frames the emergence of the classical world not as a puzzle of measurement, but as a natural, inevitable consequence of information theory and thermodynamics. It paints a picture of a universe that is constantly monitoring itself, constantly weeding out possibilities, and constantly reinforcing a stable shared reality. The journey we are about to embark on is a quest to understand this cosmic evolution. We will explore how information acts as the DNA of quantum states, how the environment acts as the unforgiving crucible of selection, and how the familiar world we know and love is the triumphant survivor of an unimaginably vast and ancient war of possibilities. The chair you are sitting on is solid, not because it was born that way, but because its state of being here has outcompeted and eliminated trillions upon trillions of other ghostly possibilities. It is a victor. Every object, every moment is a testament to this hidden cosmic struggle. The central mystery is no longer how the quantum world becomes the physical world. The question reframed by quantum Darwinism is far more elegant. How does the universe decide which reality gets to survive? Is it possible that the universe you inhabit, this solid, reliable world of cause and effect, is merely a facade that, beneath the sturdy floorboards of classical physics, lies a basement of pure, unadulterated chaos, a realm where logic frays and reality itself is a flickering ghost? This isn't a question of philosophy or metaphysics. It is the central, agonizing dilemma that birthed the modern age of science. For nearly a century, we have been haunted by a discovery so profound, so utterly contrary to our intuition, that it cleaved our understanding of existence in two. We found that the universe at its most fundamental level is built not on certainty, but on a storm of shimmering possibilities, and the bridge between that ghostly world of potential and the concrete world of our experience is a mystery we are only now beginning to solve. To understand the revolution that is upon us, we must first return to the scene of the crime, to a time when the giants of physics stared into the abyss, and the abyss stared back, presenting them with a riddle that threatened to unravel everything they thought they knew about the cosmos. The dawn of the 20th century was a time of supreme confidence. The grand clockwork of Newton's universe had been wound its gears and levers, seemingly mapping every motion from the fall of an apple to the waltz of the planets. Maxwell had tamed light itself, weaving electricity and magnetism into a single elegant tapestry of equations. For many, physics was nearing its end, a magnificent cathedral of thought with only a few final decorative stones left to be placed. But in the hushed halls of academia, unsettling cracks were beginning to appear in this perfect edifice. When scientists studied the light emitted by heated objects, the so-called black body radiation, their trusted equations broke down spectacularly. They predicted that any hot object should be radiating an infinite amount of energy, an ultraviolet catastrophe that would have sterilized the universe. Our reality quite obviously did not behave this way. There was a ghost in the machine. The man who reluctantly exorcised that ghost was Max Planck, a conservative physicist who, in a moment he later called an act of desperation, proposed a radical idea. He suggested that energy was not a smooth, continuous flow like water from a tap. Instead, it came in discrete, indivisible packets, tiny bullets of energy he called quanta. It was a mathematical trick, a fudge factor designed to make the equations work, but it was a trick that held nature's secret. This was not a triumphant discovery. It was a deeply troubling one. It was the first sign that the universe at its smallest scales played by an entirely different and far stranger set of rules. This initial insight, this quantization of energy, was the loose thread that, when pulled, would unravel the entire classical tapestry. It opened a Pandora's box of paradoxes, and peering inside were the most brilliant minds of a generation: Niels Bohr, Werner Heisenberg, Erwin Schrödinger, and their contemporaries. What they found inside was a world that defied language itself. They discovered that a fundamental particle like an electron is not a simple, tiny ball bearing orbiting an atomic nucleus. Before you look for it, before you try to pin it down, that electron exists in a state of pure potential known as a superposition. It isn't in one place. It is, in a very real sense, in all of its possible places at once. It inhabits a probabilistic haze, A cloud might be governed not by deterministic laws, but by a mathematical entity called the wave function. This wave function doesn't tell you where the electron times is asterisk. It tells you where it times might be times found if you were to look. It is a symphony of possibilities playing out simultaneously. Think of it as a spinning coin not yet landed. It is neither heads nor tails. It is a dynamic, blurry union of both outcomes, a perfect superposition. Only when the coin finally hits the table, when an interaction forces a result, does it resolve into a single definite state. This is the event that lies at the heart of the quantum mystery, the collapse of the wave function. The pioneers of the Copenhagen interpretation, led by Bohr and Heisenberg, argued that the act of measurement, the very process of an observer interacting with a quantum system, forces this cloud of potential to collapse. The universe is compelled to make a choice. The electron, which was a wave of probability spread across space, suddenly and inexplicably localizes into a single point. The ghost solidifies into a particle. But this explanation, while functional for making predictions, was profoundly disturbing. It suggested a bizarre division of the universe into two separate domains, the weird probabilistic quantum world and the solid classical world of our laboratories and our experiences. And the line between them, the act of observation. This created the infamous measurement problem, a philosophical and scientific chasm that has haunted physics ever since. The problem is that measurement is not a magical incantation. It's a physical interaction. You can't see an electron without bouncing something off it, usually a photon of light. But an electron is so vanishingly small and delicate that this interaction is not a gentle nudge. It is a cataclysmic collision. The very act of observing its position with a photon irrevocably alters its momentum, blasting it off to some new unknown trajectory. It's like trying to find the precise location of a single dust mote in a dark room by hitting it with a bowling ball. The moment you find it, you've fundamentally changed its state. Heisenberg formalized this with his uncertainty principle. The more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. You can never know both with perfect accuracy because the universe itself forbids it. The observer is not a passive spectator watching the cosmic drama unfold. You are an actor on the stage, and your presence changes the play. Nowhere is this unsettling drama more vividly staged than in the famous double-slit experiment. It is in its elegant simplicity perhaps the single most profound and mind-bending experiment ever conceived. Imagine a barrier with two thin parallel slits cut into it. On one side, you have a source that can fire single electrons one by one at the barrier. On the other side, you have a detector screen that records where each electron lands. If you close one slit and fire the electrons, they pass through the open slit and form a single, predictable band on the screen behind it, exactly as you'd expect tiny particles to behave. The same thing happens if you close the first slit and open the second. No surprises yet. But what happens when you open both slits? Classical intuition tells us we should see two distinct bands on the screen, a simple sum of the two previous results. But that is not what happens. Instead, a stunning and impossible pattern emerges on the screen. You see a series of multiple bands, an interference pattern of bright and dark stripes. This is the signature behavior of waves. It's the same pattern you'd see if you sent water waves through two openings. Where the crests of the waves from each slit meet, they amplify each other, creating a bright band. Where a crest meets a trough, they cancel out, creating a dark band. But how can this be? We are firing electrons times one at a time asterisk. There are no other electrons for them to interfere with. The only logical conclusion is as unavoidable as it is insane. Each individual electron must be passing through times, both slits simultaneously, asterisk. As a wave of potential, it interferes with itself, and only then, upon hitting the detector screen upon being measured, does it collapse into a single point-like particle. The electron seems to know. It travels as a wave of possibility and arrives as a particle of fact. This is where the mystery deepens into something approaching cosmic voyeurism. The physicists, bewildered by this result, decided to watch. They placed a tiny detector at the slits, a device capable of telling them which slit each electron actually went through. Now they could finally catch the electron in the act, and as soon as they did, the moment they peaked, the experiment changed. With the detector turned on the interference pattern, the signature of the wave vanished completely. The electrons, as if suddenly shy, reverted to behaving like simple particles. They produced just 2 bands on the screen, exactly as classical intuition predicted. The very act of observing which path the electron took forced it to choose a single path. It was as if reality itself refused to perform its magic trick while being watched. The quantum superposition was so fragile, so ethereal, that the slightest touch from the classical world, the faintest whisper of a measurement, was enough to shatter the illusion and spook the universe into a state of boring, predictable certainty. This raised a terrifyingly ambiguous question: what precisely constitutes an observer? Does it require a conscious human being with a PhD? In physics, does a simple automated camera count? What about a Geiger counter? A rock? Where is the line? The Copenhagen interpretation offered no clear answer, leaving the door open to the unsettling idea that consciousness itself was somehow the agent responsible for collapsing the quantum wave, function for turning possibility into reality. This was a notion that repulsed many scientists, including the great Albert Einstein. He could not accept a universe that remained in a state of suspended animation until a conscious mind decided to look at it. He famously derided the probabilistic nature of it all, stating, "God does not play dice with the universe." He believed there must be a deeper, more orderly reality hidden beneath the quantum weirdness, some hidden variables that would restore the comfortable causality of the old world. To highlight the sheer absurdity of applying the Copenhagen interpretation to the world we actually live in, Erwin Schrödinger conceived of his legendary and macabre thought experiment. He asked us to imagine a cat placed inside a sealed, opaque steel box. Alongside the cat is a diabolical device, a tiny piece of radioactive material so small that in the course of an hour there is a perfect 50/50 chance that just one atom will decay. If it does decay, it triggers a Geiger counter, which in turn releases a hammer that smashes a vial of hydrocyanic acid, killing the cat instantly. If the atom does not decay, the cat remains alive. The box is sealed. We wait an hour. According to our classical intuition, the cat inside is either alive or dead. We just don't know which one until we open the box. But according to a strict application of quantum mechanics, this is wrong. The radioactive atom unobserved is in a superposition of both states. It has both decayed times and times not decayed. And because the cat's fate is inextricably linked to the state of this quantum atom, the cat itself must also enter this ghostly realm. It is not alive times or times dead. It is in a ghastly, smeared-out state of being both perfectly alive times and times perfectly dead at the very same time. Its wave function is a mathematical union of these two contradictory realities, a grotesque superposition of existence and non-existence. It is only when we, the observer, open the box and make a measurement when we look that the wave function of the entire system collapses. In that instant, reality is forced to choose. The universe flips its coin, and we are confronted with either a living pet or a tragic corpse. Schrödinger did not propose this as a serious possibility. He intended it as a form of protest, a sarcastic and brilliant illustration of the chasm between the microscopic quantum world and the macroscopic world of cats, boxes, and poison. How, he asked, does the smear of quantum possibilities transition into the single definite reality we experience every moment of our lives? This became the central battleground for the soul of physics. On one side, Bohr and his followers accepted the paradox, suggesting we simply had to abandon our classical intuitions about reality. The world just times is times that's strange, and our role as observers is an inextricable part of it. On the other, Einstein, Schrödinger, and others searched for a more complete theory, one that could explain times why times a measurement produces a single outcome without resorting to this seemingly magical collapse. But there was an even deeper, more subtle mystery buried within the measurement problem, one that is often overlooked. It's not just that a measurement produces times a times definite outcome, it's that it produces times the same times definite outcome for everyone. Think back to Schrödinger's box. When you open it and see a living cat, your friend standing next to you also sees a living cat. The newspaper report the next day will state the cat survived. The history books will record it as such. There is a universal consensus. But why? According to the Copenhagen Interpretation Times, your time's observation collapsed the wave function. But why is your collapse binding on everyone else? Why doesn't your friend's observation have an equal chance of collapsing it to the dead cat state? How does the universe ensure that all subsequent observers agree on the same shared classical fact? This problem of objective reality, the creation of a consensus view from a private quantum interaction, was a profound weakness in the old theory. It was an embarrassment swept under the rug, a puzzle that hinted at a missing piece of the cosmic machinery. The pioneers had given us a description of times, what times happens, but not times how times or times why asterisk. They had left us with a universe built on a foundation of sand, a reality held together by the mysterious and ill-defined act of being watched. For decades, this was where the story stalled. The quantum world remained an isolated island of strangeness, governed by its own bizarre laws, while the classical world of our experience seemed to operate on an entirely different, more sensible plane. The bridge between them remained shrouded in fog, a collapse that happened for reasons no one could explain, creating a single agreed-upon reality through a process no one understood. The scientific community was left grappling with a fundamental disconnect, a schism running through the heart of nature itself. They were like cartographers who had mapped two separate continents with exquisite precision, but had no idea what lay in the vast, unexplored ocean that separated them. A new generation of physicists would be needed to sail into that unknown ocean. They would have to question the most sacred assumption of the original theory, the special role of the observer. What if the observer wasn't special at all? What if reality itself, in all its messy, chaotic glory, was doing the observing constantly, relentlessly, and everywhere at once? A new idea was stirring, a theory not of collapse, but of selection. A theory that didn't need a conscious mind to forge a universe from the quantum fog, but instead found the answer in the simple, brutal logic of survival. And so we find ourselves straddling two realities. One, a ghostly, indeterminate realm of pure potential where a single particle can exist in countless places at once, a shimmering phantom of probability. The other, our world, solid, definite, a world of granite mountains and falling rain where a cat is either alive or it is dead, but never both. For a century, the chasm between these two worlds has been the deepest, most unsettling mystery in all of physics. If the universe, at its most fundamental level, is governed by the ethereal laws of the quantum, why does the world we experience appear so resolutely, so stubbornly classical? Where does all that strange, beautiful weirdness go? The answer, it turns out, is not that the quantum rules are switched off for larger objects. They are never switched off. Instead, they are drowned out. They are silenced by a relentless, invisible, and universal process. A process that begins the instant any quantum system, no matter how small or simple, touches the outside world. This process is the universe's great secret keeper, its enforcer of certainty. It is called decoherence. To understand it, you must stop thinking of the environment as a passive backdrop, a quiet stage upon which the quantum drama unfolds. The environment is the most active, intrusive, and nosy character in the entire cosmic play. Imagine a single, perfect tuning fork, forged in an impossible void, completely isolated from everything. When struck, it vibrates with a pure, singular tone. This is our quantum system in a pristine superposition, a clear, unadulterated state of A and B existing together. Its quantum nature, its coherence, is perfect. Now let's release that tuning fork into our world. What happens? Air molecules, trillions upon trillions of them, immediately begin to bombard it. Each tiny collision, insignificant on its own, is a minuscule act of measurement. Each air molecule that bounces off the fork carries away a tiny fragment of information about the fork's vibration, its position, its momentum, its phase. These are not conscious observers. They are simply spies. Unwitting, microscopic spies that are everywhere all the time. The universe is teeming with them. Photons from the nearest light source stray heat radiation from distant walls. Even the subtle gravitational pull of the Earth itself. Every single interaction is an act of eavesdropping. The pure singular tone of our tuning, for its perfect coherence, begins to degrade. It's no longer a solo performance. The information about its state is no longer its own. It has been leaked, smeared, and broadcast into the chaotic static of the surrounding environment. The pure note dissolves into a meaningless hiss of white noise. Its superposition hasn't been chosen or collapsed in the old sense. It has been obliterated by a billion tiny informational cuts. Its delicate quantum signature has been washed away in a flood of environmental noise. This, in essence, is decoherence. It is the constant, unrelenting leakage of quantum information from a system into its environment. This informational assault is happening to you right now. As you sit there, you are being measured on a scale that defies comprehension. Quintillions of photons from the light in your room are bouncing off your skin every single nanosecond. More than a septillion air molecules are colliding with you every moment, each one registering your position with brutal precision. The chair you're sitting on is a massive network of atoms all interacting with your own. Their thermal vibrations are constant census of your physical state. You are not a closed system. You are the most open, most interrogated, most thoroughly measured object imaginable. Any quantum superposition you might have possessed at the moment of the Big Bang was decohered away in a time frame so infinitesimally small it makes a lightning strike look like an eternity. This is why we never see a cat in a superposition of alive and dead. The cat is simply too big, too warm, too complex. It is coupled to its environment in an incalculable number of ways. The very air it breathes, the light that illuminates its fur, the ground beneath its paws, the cosmic microwave background radiation streaming through it from the dawn of time, all of these are environmental spies. They are constantly measuring the cat's state. Is its heart beating? Is its body temperature 38 degrees Celsius? Is it breathing? The information answering these questions, yes or no, is instantly and irrevocably imprinted upon countless photons and air molecules, which then fly off at the speed of light, carrying that data into the wider universe. The quantum secret of the cat's superposition, if it ever existed at all, is a secret that cannot be kept. It is broadcast across the cosmos in less than a trillionth of a second. To try and put the cat back into a superposition would be like trying to unring a bell that has been heard in a neighboring galaxy. You would have to track down every single one of those trillions of photons, every one of those scattered air molecules, and reverse their journey, erasing the information they carried without disturbing anything else. It is a task not just practically, but cosmically impossible. Decoherence ensures that for any object large enough for us to see its quantum nature is a fleeting ghost, a whisper that vanishes before anyone is there to hear it. Let us consider another, perhaps more poignant analogy. Imagine quantum entanglement, that spooky action at a distance that so troubled Einstein as a secret message. A profound truth written with delicate ink on a single fragile sheet of paper shared between two trusted friends. As long as the paper is safe, the message is coherent, and the bond between the two friends, the entanglement, is perfect. Now imagine a single drop of water falls upon the page. The ink begins to run. The message blurs. A single word becomes illegible. The coherence is damaged. Decoherence is not a single drop of water. It is a torrential, unending rainstorm. The environment doesn't have to understand the secret message. It doesn't need to read it or interpret it. It just has to touch the paper. Each interaction, each photon bouncing off one of the entangled particles, is another drop of water further smearing the ink. Very quickly, the secret message is no longer a message at all. It's just a meaningless, chaotic stain. The profound correlation between the two friends is gone, not because it was magically broken by a conscious observer, but because the very medium upon which it was written has been corrupted by its contact with the outside world. The entanglement has bled away into the environment. The spooky private connection has been dissolved into a public, noisy mess. This is why building a quantum computer is so monumentally difficult. Engineers must become the ultimate guardians of secrets, building pristine, isolated chambers colder than deep space, shielding their delicate quantum bits, or qubits, from the slightest stray photon, the most minuscule vibration. They are fighting a constant losing battle against the universe's most powerful force of conformity decoherence. Through this lens, the transition from the quantum to the classical world is not a magical leap, but a brutal process of natural selection. In the chaotic, information-hungry environment of our universe, only certain states are robust enough to survive. Think of a spinning coin. While it's in the air, it is in a superposition of heads and tails. It is both, and it is neither. This is its coherent quantum state. The moment it hits the table, the moment it interacts strongly with its environment, that superposition is destroyed. It is forced to choose. But which states does it choose between heads or tails? It doesn't land in a state that is a blurry half-heads, half-tails mixture. Why? Because heads and tails are the two most stable, predictable, and informationally redundant states the coin has. They are the states that best survive the interrogation of the table's surface. These resilient states are what physicists call pointer states. They are the classical realities that are left over after the storm of decoherence has washed everything else away. The environment, through its constant measuring, effectively selects for these pointer states. It favors states that are stable and that imprint clear, unambiguous information about themselves onto their surroundings. A planet's position in its orbit is a pointer state. The fact that a chair is solid is a pointer state. These are the aspects of reality that remain stable and predictable, even under the universe's relentless observational glare. The countless other, more exotic quantum possibilities are far too fragile. They are like frost patterns on a window pane, infinitely complex and beautiful, but doomed to vanish with the first light of dawn. Decoherence, then, is a monumental breakthrough. It solves half the mystery. It explains with chilling efficiency times why times we don't see large-scale quantum effects. It tells us why our world appears classical. The universe, through environmental monitoring, enforces a kind of classicality on any system large enough to be monitored. It is a mechanism of purification, stripping away the ghostly ambiguities of the quantum world and leaving behind a skeleton of reliable classical facts. It transforms the quantum world of maybe into the classical world of is. It explains the transition. It bridges the chasm, and yet a profound and unsettling question remains. A question that decoherence, for all its power, cannot answer on its own. Decoherence shows us how times a system loses its quantumness and is forced into a menu of possible classical outcomes. For Schrödinger's cat, the environmental spies kill the superposition, forcing a resolution into one of two pointer states, alive or dead. The quantum blur is gone, replaced by a classical probability. 50% chance of a live cat, 50% chance of a dead one. But it doesn't tell us which times of those outcomes is the one that is actually realized in our world. It presents us with the menu of possible classical realities, but it never tells us which one will be served for dinner. When you open the box, you don't see a probability. You see a cat, a single cat, either alive or dead. And here is the true heart of the puzzle. Your friend looking over your shoulder sees the exact same thing. Everyone in the universe who might later learn of the result will agree on the outcome. We all inhabit a single, consistent classical reality. Decoherence successfully explains why the menu of possibilities is restricted to classical options, but it says nothing about how or why a times single, one times of those options is unanimously chosen and agreed upon by every observer. It gets us to the doorstep of the classical world, but it doesn't give us the key to get inside. It leaves us with a universe that has shattered into countless parallel classical storylines, with no explanation for why we find ourselves in this particular one. There must be another layer to the process, a mechanism not just for eliminating the quantum, but for selecting and broadcasting the classical. A new principle that explains how the environment does more than just destroy secrets. A principle that explains how the environment actively collaborates in creating a consensus reality, an objective physical world that we can all study, share, and agree upon. The chaotic noise of decoherence is just the first act. The true magic happens in how that noise is structured, how the information leaked into the world is copied, duplicated, and spread, creating redundant records of a single classical truth. We need a theory for how nature doesn't just eliminate possibilities but forges an agreement. We need a theory of quantum Darwinism, and so decoherence had left us stranded. It provided a powerful, almost brutal explanation for why the delicate ghosts of the quantum world vanish from our sight. The universe, through its constant chaotic chatter of particles and photons, acts as an inescapable observer, collapsing possibilities into fragile, fleeting actualities. But in solving one great mystery, the disappearance of superposition, it had inadvertently created another one that cuts even deeper into the heart of our perceived reality. If the environment forces a quantum system to choose, why do we all see it, make the same choice? When the lid on Schrödinger's box is finally lifted, you see a living cat. I see a living cat. A camera recording the event shows a living cat. We don't just agree. Our consensus is the very definition of objective reality. Decoherence alone in its raw form offered no guarantee of this. In its silent mathematics, there was still room for a universe of private realities, a multiverse of observers, each collapsing their own version of the world, never to be reconciled. The theory explained why you couldn't see a cat that was both alive times and times dead, but it failed to explain the profound cosmic consensus that we all see a cat that is simply unequivocally times alive asterisk. The bridge from the quantum to the classical was half-built, dangling over a terrifying chasm of subjectivity. To complete it, physics needed more than just a mechanism for destruction. It needed a principle of creation. It needed a new kind of genesis. The revolution we were waiting for arrived not with a thunderous bang, but with a quiet, profound shift in perspective. It required us to look at the very agent of destruction, the environment, and see it in a completely new light. For decades, we had imagined the environment as a quantum wrecking ball, a mindless storm of interactions that smashed delicate superpositions into pieces, stealing their information and scattering it to the winds where it could never be recovered. This was the narrative of loss of quantum coherence bleeding out into the cosmos. But what if this picture was fundamentally wrong? What if the environment wasn't a vandal but a witness? What if it wasn't a thief but a broadcaster, an immense universal copying machine? This was the pivotal insight, the conceptual leap that would finally begin to illuminate the dark passage. From the quantum realm to our shared solid world, the idea began to form that the environment doesn't just destroy information, it filters it, it selects it, and most crucially, it times, amplifies, times it. This process, it turns out, is not random, it is discerning. It is in a way that would prove shockingly familiar, a form of natural selection acting not on organisms, but on the very information that constitutes reality itself. At the heart of this radical reimagining is a physicist who spent a lifetime wrestling with the ghost in the quantum machine Wojciech Zurek. Working for decades at the Los Alamos National Laboratory, a place born from the raw power of the atom, Zurek was uniquely positioned at the frontier where the quantum and the classical collide. He was a student and collaborator of the legendary John Archibald Wheeler, a man who gave us concepts like the black hole and the wormhole, and who instilled in Zurek a relentless drive to ask the biggest, most foundational questions. Zurek was haunted not just by the mathematics, but by the physical intuition of the problem. He understood the power of decoherence, having been one of its pioneering theorists, but he also felt its profound incompleteness. He knew that the shared objective nature of our world, the fact that a table is a table for everyone, that the moon hangs in the same sky for all of us, was a non-negotiable feature of reality. Any fundamental theory had to explain it. It wasn't enough to say that quantum possibilities fade. He needed to know which possibilities survive and why those survivors become the bedrock of everyone's experience. He searched for a physical principle that could explain this cosmic agreement, a law of nature that could build a stable classical consensus out of the fleeting quantum foam. His quest led him to a powerful analogy, one borrowed from a seemingly distant field of science, yet one that deals with the very same principles of information, survival, and environment, Darwinian evolution. And from this cross-pollination of physics and biology, a new theory was born. A theory with a name that is as evocative as it is precise: Quantum Darwinism. The central idea is a stunning inversion of our old thinking. We had believed the environment was a place where quantum information went to die, Zurek proposed the opposite. The environment is the ultimate proving ground, where certain quantum states are tested for their fitness. And what is fitness in this quantum context? It isn't strength or speed or intelligence. It is quite simply the ability to be copied. The ability to imprint your information onto the environment so effectively, so redundantly that you leave behind an undeniable public record of your existence. Just as a successful gene is one that makes countless copies of itself, ensuring its survival across generations, a successful quantum state is one that imprints countless copies of its information into its surroundings. It is a selection process governed not by the survival of the fittest organism, but by the survival of the fittest information. To grasp this, we must first understand what makes a quantum state fit for this process. Not all states are created equal. An electron in a superposition of spin up and spin down is an ethereal, fragile thing. The slightest nudge from a passing photon can disrupt the delicate balance. But some states are inherently more robust, more stable in the face of environmental interrogation. Zurek gave these privileged states a special name: pointer states. Think of a spinning coin. While it's spinning, it's in a superposition of heads and tails. Its state is ambiguous, delicate, and easily disturbed. A single interaction with the table will collapse it into one of two definite outcomes. Now imagine that same coin lying flat on the table, either heads up or tails up. This state is stable. It is robust. You can bump the table, shine a light on it, blow air across it, and it will remain heads or tails. Its information is resilient. Pointer states are the quantum equivalent of that flat coin. They are the preferred configurations that a quantum system naturally settles into when interacting with its environment, because they are the most stable against further disturbance. For our electron, these would be the definite states of spin up or spin down. For Schrödinger's cat, these would be the definite physiological states of alive or dead. These are the states that don't just survive the environment's relentless questioning. They are the only states capable of providing a clear, unwavering answer. But stability is only the first part of the story. The true genius of quantum Darwinism lies in what happens next. The environment doesn't just nudge the system into one of its pointer states. It then begins to act like a vast, decentralized press office. Every photon that bounces off the system, every air molecule that collides with it, every stray particle that interacts with it becomes a messenger. It doesn't just interact and fly away, its memory wiped clean. Instead, it picks up a tiny fragment of information about the pointer state of the system and carries it away. A photon that scatters off a living cat carries with it information about the cat's position, its temperature, its movement. A different photon scatters off a different part of the cat, carrying away a similar, slightly different fragment of the same story: the cat is alive. An air molecule bumps into its fur and recoils in a way that is minutely dictated by the cat's living warmth. Each of these interactions creates a record, a tiny independent copy of the system's state, now encoded in a fragment of the environment. The environment, this thing we once saw as a chaotic void, is in fact a vast dynamic medium, becoming saturated with information. This leads us to the heart of the Darwinian process redundancy, the sheer overwhelming power of numbers. It's not one photon or one air molecule that carries this information away. It's trillions upon trillions of them every single microsecond. Each one becomes an independent witness, a carrier of a partial but consistent truth. The environment is flooded, carpeted with countless redundant copies of the pointer state's information. It's the difference between a secret whispered once in a crowded room and a headline printed in billions of newspapers and broadcast on every television screen across the globe. The secret is fragile, subjective, and easily lost. The headline is robust, objective, and unavoidable. The pointer state, the cat is alive, achieves its classical status, not because it is special in and of itself, but because its information has been copied, broadcast, and stored with such colossal redundancy throughout its local environment, that it becomes public knowledge. It becomes a fact. You can intercept a tiny fraction of these environmental messengers, the photons entering your eye, for instance, and you will decode the same message. I can stand across the room and intercept a completely different set of photons, and I will reconstruct the very same fact. The camera intercepts another set, A mouse in the corner intercepts yet another. We all agree on the state of the cat because we are all independently tapping into this immense publicly available database of information that the cat has imprinted upon the universe around it. Now the analogy to biological evolution snaps into sharp, stunning focus. In biology, the gene is the fundamental unit of information. Organisms are merely the temporary vehicles that carry and express these genes. The environment is the selective filter. It determines which organisms, and therefore which genes, are successful enough to reproduce. The currency of success is replication, making copies that persist into the next generation. In quantum Darwinism, the pointer state is the fundamental unit of stable information. The quantum system, the cat, the electron, is the vehicle for that state. The surrounding environment is the selective filter times the medium for reproduction. But here, reproduction isn't about creating new organisms. It's about creating informational clones, imprinting the pointer state's data onto countless environmental fragments. The fittest states are those that are most adept at this imprinting process. They are the states whose information proliferates, creating a massive, redundant record that can be accessed by any observer. The unfit states, the delicate superpositions, are evolutionary dead ends. They are incapable of creating stable, widespread records of their existence. They cannot reproduce their information effectively into the environment, and so, like a species that cannot adapt their information, lineage vanishes from the public record. They remain forever in the private, unobservable quantum realm. What this paints is a picture of reality itself being the outcome of a cosmic competition. Our classical world is not some fundamental pre-existing stage on which quantum events unfold. Instead, it is the winning story, the version of reality whose information was so robust, so fit, that it managed to replicate itself across the environmental medium more effectively than any other competing possibility. The solidity of the chair you're sitting on, the steady light from the lamp, the very screen you are watching, these things feel real and objective to us because they have won the quantum Darwinian game. They are masters of informational replication. Their pointer states have successfully saturated our shared environment with so many copies of their information that their existence is a matter of overwhelming public consensus. The ghostly might-have-beens, the superpositions of the chair existing here, and also a meter to the left, have lost. They failed the fitness test. They could not create a durable, redundant record, and so their information was scattered into useless, incoherent noise, never to form the basis of a shared classical fact. Our objective reality is a mosaic of these informational survivors. It is a document written and rewritten, copied and cross-referenced by trillions upon trillions of photons and particles every instant. It is the most successful story the universe has ever told about itself. And so we revisit Schrödinger's tormented cat one last time, but now armed with this new powerful perspective. Inside the box, before any information can leak out, the cat coupled to the quantum trigger truly is in a superposition of alive times and times dead. It is a fragile, private quantum state. But the moment the lid is opened, or even the moment the tiniest amount of heat or a single photon leaks out, the process begins. The environment starts to interrogate the system. It quickly and violently forces a choice between the two most stable, robust pointer states available, the complex physiological state of alive and the equally complex state of dead. Let's say the outcome is alive. Instantly, the Darwinian machine kicks into gear. The living cat, a warm breathing system, begins to broadcast information about its aliveness into the box. It radiates infrared photons. It warms the air molecules around it. It makes tiny sounds. Every fragment of the environment that interacts with it becomes a carrier for the single consistent message alive. Trillions of copies are made in a fraction of a second, flooding the local environment. When you and I finally look inside, we are not collapsing the wave function. We are simply passive readers. We are accessing the already published headline. We are intercepting a few of the countless informational copies that have already proliferated and established the objective fact of the cat's state. We agree because we are both reading from the same universally available cosmic newspaper. The mystery of consensus is solved. Objectivity is not something we create with our minds. It is something we discover from the redundant records left by the quantum world's own internal selection process. Quantum Darwinism then has finally completed the bridge. It shows us how the definite objective classical world we all share can emerge directly from the uncertain probabilistic quantum substrate without any need for a conscious observer to play a special role. We are not the authors of reality, we are merely its audience. But this revelation, as profound as it is, throws open a new set of doors leading to even deeper questions. It provides a powerful theoretical framework, an elegant and compelling story for how the world comes to be. But is it just a story? If this process is truly happening, if the environment all around us is truly humming with these redundant copies of quantum information, then where are they? Can we intercept these messengers? Can we read the fine print of reality being written in real time? Can we, in the laboratory, actually catch this cosmic selection process in the act and prove once and for all that our world is truly built upon the survival of the fittest information? The theory is on the table. The next great challenge is to find its footprints in the sand. And so the quantum world makes its choice. Through the relentless trial of decoherence, only the most stable, the most robust, the most classical-like states are permitted to endure. These pointer states, as we've called them, are the survivors of a brutal environmental selection, the victors in a microscopic war for existence. But their survival alone does not solve the deepest riddle of our experience. It explains why a single outcome is chosen, but it does not yet explain why it becomes times our times outcome. It doesn't explain the unshakable consensus of reality itself. Look at your hand. Now imagine a friend across the room does the same. You both see a hand. You agree on its shape, its position, its stillness. This agreement feels trivial, automatic, the most basic fact of the world. Yet within the framework we've been exploring, it is anything but. How does the universe enforce this absolute unanimity? How does the outcome selected for a quantum system in one corner of a room become the objective, undeniable truth for everyone else who enters it? The answer does not lie in some mystical connection between our minds. It lies in the environment itself, which plays a second, even more profound role. It is not merely the judge, jury, and executioner of quantum states. It is also the press, the town crier, the universal broadcaster, ensuring the verdict is known by all. To understand this, we must grasp one of the most elegant ideas in modern physics, redundant encoding. It sounds technical, yet it is a concept of sublime simplicity. The universe, it turns out, is a relentless gossip. When the environment interacts with a quantum system and selects its pointer state, the location of a dust particle, the spin of an electron, it doesn't just keep that information to itself. It makes copies, not one or two, not 1,000. It makes countless trillions upon trillions of copies, and it hurls them out into the world. The environment acts as a colossal natural printing press, and the information about the system's chosen state is its headline story. Let us imagine a single grain of dust floating in the deep void between galaxies. In the pure quantum description, before any meaningful interaction, its location is a hazy cloud of probability. But it is not truly alone. It is swimming in a sea of ancient light, the cosmic microwave background. Photons, the fundamental particles of this light, are constantly colliding with it. Each and every photon that strikes our dust grain and scatters off is subtly changed by the encounter. It now carries with it a tiny, indelible record of where that collision happened. The photon has become a witness. It holds a single microscopic copy of the information the dust grain was times here asterisk. This is not a gentle or isolated process. Billions of photons per second might ricochet off this single grain. Air molecules, if our grain were in a room, would do the same, jostling against it and carrying away a kinetic memory of its position. Even the faint tendrils of gravity emanating from the grain itself stretch across space-time, encoding its location in their very fabric. Each of these interactions creates another copy, another witness. The state of the dust grain, its pointer state of position, is not recorded just once. It is redundantly encoded over and over and over again into innumerable independent fragments of the surrounding environment. Think of it like this. Picture a grand, ornate statue hidden in the center of a pitch-black cavernous hall. The statue itself is the quantum system, and its true definite shape is its pointer state. The air in the hall is thick with an impossibly fine, weightless dust. These are the particles of the environment. If you were to shine a colossal floodlight on the statue for just a fraction of a second, the light would bounce off its surface and scatter in all directions. Each particle of light, each photon, would now carry a fragment of the statue's image. One might carry the glint from an eye, another the curve of a shoulder, a third the shadow from a fold in its robe. The air of the great hall is now filled not with the statue itself, but with a quadrillion fleeting light-born portraits of it. This is the essence of redundant encoding. The information about the statue's shape has been broadcast imprinted onto the very medium of the hall. Now, you don't need to see the statue directly to know its form. You could stand anywhere in that hall, cup your hands, and collect a tiny fraction of the scattered light. From that sample alone, you could reconstruct the statue's appearance with near-perfect fidelity. A second person standing on the opposite side of the hall could do the exact same thing. They would collect a completely different set of photons, a separate and independent sample of the environmental record. And yet their conclusion would be identical to yours. They would reconstruct the same statue, a third person, a fourth, 1,000 people, all sampling different parts of the scattered light, would all without fail arrive at the same shared truth. They agree not because they are all looking at the original statue, but because they are all looking at the overwhelmingly abundant, consistent and faithfully copied information times about times, the statue that has saturated its environment. They agree because the evidence is inescapable. This is how objectivity is born. Objectivity is not a property of the object itself. It is a property of the information times, about times the object, and its prolific, redundant broadcast into the cosmos. This is the genius of quantum Darwinism. The observer you is no longer a mystical figure endowed with the power to collapse reality with a glance. You are demoted in the most beautiful way imaginable to being just another piece of the environment. Your eyes are simply magnificent photon detectors. When you look at an object, you are not performing some profound quantum act. You are passively intercepting a tiny fraction of the trillions of informational copies that the object has already imprinted upon the photons streaming away from it. You are, in a very real sense, reading the public record. The reason reality feels so solid, so classical, is because this public record is impossibly vast and consistent. Consider a simple object like a tennis ball sitting on a table. The number of photons from the room's lights scattering off it every microsecond is beyond astronomical. Each one carries away the news. The ball is here, it is yellow, it is round. That information is relentlessly copied into the surrounding air molecules that bump against it, into the infrared radiation it emits, into the very pressure it exerts on the table. The tennis ball is screaming its classical state into the universe with a bandwidth that dwarfs all of our human technology combined. To disagree on the position of the tennis ball, you would have to somehow intercept a set of environmental fragments that told a different story. But such a story doesn't exist. The alternative quantum possibilities, the superposition of the ball being in two places at once, were never stable enough to be printed. They were ephemeral, delicate quantum ghosts washed away by decoherence before they could ever leave their mark on the environment. Only the fittest pointer state survived long enough to have its story told, and that story was then copied with such staggering fidelity and volume that it became the only one available to be read. What we call a classical fact is simply information that has been so redundantly encoded into the universe that its truth becomes a matter of overwhelming statistical certainty. This process resolves one of the deepest paradoxes of the Schrödinger's cat experiment. Why does everyone who looks in the box agree on whether the cat is alive or dead? The answer is that the state of the cat, its physiological condition, is being constantly monitored by its environment long before we ever open the lid. The air molecules in the box, the infrared photons radiating from its body, the vibrations it transmits to the floor, all these things are constantly creating redundant records of its state. A living cat breathes, its heart beats, its body is warm. Each of these processes bombards the environment inside the box with an avalanche of information declaring alive, alive, alive. A dead cat is still cold and silent, broadcasting a very different, but equally definitive message. When you finally open the box, you are not collapsing the cat's wave function, you are merely accessing the final headline of a story that was written, edited, and published trillions of times over within the box's sealed environment. You and anyone else who looks will agree, because you are both accessing the same broadcast, the same mountain of evidence pointing to a single, unambiguous conclusion. The choice was made long before you arrived. You are just the last one to hear the news. The environment in this sense acts as a vast, decentralized memory bank for the universe. It is a cosmic hard drive, and classical facts are the files that have been saved with near infinite backup copies. This cascade of information flows outward from every single object at every single moment. The Earth itself is broadcasting its position, its rotation, its very existence through its gravitational field and its reflected light. Every photon of sunlight that bounces off the Pacific Ocean carries with it a bit of data saying water exists here. Every neutrino that passes through the planet's iron core is subtly affected, becoming another messenger carrying news of the core's density and temperature. We are swimming in an ocean of such information. It is the invisible scaffolding upon which our shared reality is built. We can even begin to quantify this. Physicists can calculate how quickly information about a system's state leaks out into the environment. For an object the size of a single dust mote, its location is so thoroughly recorded by scattered photons that any quantum superposition of its position would vanish in less than a nanosecond. For a human-scale object, that time becomes fantastically shorter, so brief that it has no physical meaning. The classical world we perceive is classical precisely because it is the world of systems that are too large, too complex, and too interactive to keep their quantum secrets to themselves. They are constitutionally incapable of privacy. Their states are public knowledge published on a timescale that makes the blink of an eye feel like an eternity. This perspective recasts the entire universe. It is not a silent, static stage on which events unfold. It is a dynamic, seething network of information exchange. Every interaction is a transaction of data. Every particle is a potential carrier of a message. Reality is a constant, ongoing conversation between systems and their environments, and the laws of physics in this view are the syntax and grammar governing that conversation. The classical world emerges as a symphony of consensus, where countless tiny voices, the echoes and imprints on photons and air molecules, all sing the same song. The fuzziness and uncertainty of the quantum realm are still there, underpinning everything, but we can't perceive them directly for the same reason. You can't hear a single person whispering in the middle of a roaring stadium. The roar of classical information is simply too loud. It is a humbling realization. Our perception, our sense of a solid and reliable world, is a derivative experience. We are latecomers to the scene of the crime, detectives arriving to find the story of what happened already written in the scattered dust and the ambient light. We piece together the narrative from the clues the universe leaves for us, clues that are so abundant and so consistent that we mistake them for the event itself. We have built our entire civilization on the reassuring bedrock of this shared objective reality. But now we see it for what it is, the magnificent emergent consequence of a universe that cannot stop talking about itself, a universe where the most robust truths are simply the stories that have been told the most times. This flow of information, however, is not always perfect. The environment is the medium, but what happens when that medium is thin or distorted? What happens when the witnesses are few and far between, when the broadcast is faint and riddled with static, in those desolate corners of the cosmos, or in the pristine silence of our laboratories? The symphony of consensus can falter. And in that quiet, when the classical truth is no longer being shouted from the rooftops, something else, something far stranger, is given the chance to be heard. And so, we stand at the precipice of the Great Divide. We have witnessed the phantom-like existence of a quantum system, a creature of pure potential living all possible lives at once. We have watched as the relentless chaotic chatter of the universe, the process we call decoherence, forces this creature to abandon its ghostly multiplicity. The quantum mirror shatters, the superposition dies, but this death, as we have seen, is not the full story. It is a demolition, not a construction. It clears the stage, but it does not write the play. Decoherence tells us why we can no longer see the cat as both alive times and times dead, but it has remained stubbornly silent on the most crucial question of all. Why do we all, every single one of us, agree that the cat is specifically alive times? Why is your reality and my reality and the reality of a distant observer on a passing starship all locked into the same single concrete fact? The demolition crew has done its job, but the architect has yet to reveal the blueprint for our shared classical world. How is this universal consensus forged from the ashes of quantum possibility? The answer, the unifying principle we have been searching for, is one of the most beautiful and powerful ideas in modern physics. It is a concept that elevates the environment from a simple brutish vandal into the universe's most meticulous and prolific biographer. It is called Quantum Darwinism. The name itself is a profound hint, evoking a grand cosmic process of natural selection. But what precisely is being selected? It is not a species, not a creature of flesh and bone. It is something far more fundamental. It is information itself. Quantum Darwinism proposes that only the fittest information about a quantum system can survive the perilous journey from the quantum realm to our classical world. Only the most robust, most stable, most reproducible information can successfully proliferate throughout the environment, becoming the objective fact we all observe. All other information, all the delicate, ghostly details of the superposition, is simply too fragile to endure. It is weeded out, rendered extinct by the sheer act of being observed by the cosmos. This is not a passive filtering. It is an active, competitive, and utterly ruthless process of selection. To understand how this selection unfolds, we must radically reimagine the environment. We have until now pictured it as a noisy, featureless bath, a disruptive sea of random interactions. But Quantum Darwinism invites us to see it for what it truly is, an unimaginably vast and vigilant surveillance network. Every single particle that bumps into our quantum system, every photon of light, every molecule of air, every stray thermal vibration is not just a random nuisance. It is a spy, a microscopic agent, an infinitesimal journalist that interacts with the system and then flies away, carrying with it a fragment of information about the state it was in. The universe, in its relentless curiosity, is constantly photographing the quantum world, using trillions upon trillions of tiny single-pixel cameras every single instant. This cascade of interactions creates a blizzard of data, an informational storm that engulfs the system, and it is within this storm that the principle of selection takes hold, separating the immortal fact from the fleeting fantasy. The key to this entire process lies in those special, stable configurations we have come to know as pointer states. These are the robust, classical-like states of a system particle. At times this time's position, not that one. Atoms spin pointing times up, times not down. They are the informational bedrock. When a photon, our tiny spy, glances off a system that is in a pure pointer state, say an electron at a definite location, it picks up a clear, unambiguous piece of information. The photon's trajectory is now correlated with the electron's position. It carries away a faithful high-fidelity record the electron was here. Another photon comes along and does the same, and another, and another. Soon, countless photons, air molecules, and other environmental particles have all interacted with the electron and have all left carrying the exact same piece of information. They have each become a tiny independent record, a single-entry notebook that reads, "The electron was here." But what happens when our spy encounters a system in a delicate superposition, the state of being in multiple places at once? The information it gleans is now a muddled, complex, and profoundly fragile quantum state. The photon becomes entangled with the time's entire time's superposition. It now carries a strange hybrid message, a quantum whisper, that says the electron was here and there. This entangled information is extraordinarily vulnerable. The slightest subsequent interaction will destroy it. It is a secret written in disappearing ink. While the information about the pointer state is simple, robust, and easily copied, the information about the superposition is complex, delicate, and virtually impossible to reproduce faithfully. It cannot withstand the brutal editing process of the cosmos. It is in Darwinian terms unfit. It possesses no survival advantage. And so the universe selects for the simple, the stable, the communicable. This leads us to the conceptual heart of quantum Darwinism, the creation of redundant records. As the environment relentlessly monitors the system, it doesn't just make one copy of the pointer state information, it makes an astronomical number of them. Think of a grand statue standing in a public square. 1,000 people take its picture from 1,000 different angles. Each photograph is a separate, independent record of the statue's existence and form. While each picture is unique in its perspective, they all contain the same core redundant information. The statue is here and it looks like this. Now imagine our quantum system is the statue, the environment is the crowd of 1 trillion photographers. Each photon and air molecule is a camera, and each one captures the state of the system. The information about the stable pointer states gets copied again and again and again, imprinted onto countless particles that scatter into the wider universe. This vast, redundant encoding is the birth of objectivity. This is the moment a private quantum fact becomes a public classical reality. The reason you and I and everyone else agree on the outcome of a quantum measurement is because we are not, in fact, looking at the quantum system itself. That is impossible. The system is forever veiled from us. Instead, we are sampling the environment. We are, in effect, intercepting a few of the countless spies that have flown away from it. When you look at a table, your eyes are not absorbing the table's quantum wave function. Your eyes are absorbing photons, environmental spies that have bounced off the table. Because trillions upon trillions of those photons are all carrying the exact same, redundantly encoded information about the table's position, shape, and color. Its pointer states, the message you receive is overwhelmingly consistent, stable. You could look at a tiny fraction of those photons, and I could look at another tiny fraction, and we would both reconstruct the exact same image. We agree because we are both reading from different pages of the same book, a book whose every page has been copied and reprinted 1 billion times over a cosmic bestseller distributed freely throughout the universe. Objectivity, then, is not some intrinsic property of the world that exists in a vacuum. It is a consensus, a shared agreement forged by information. It is an emergent phenomenon born from the constant, relentless monitoring of a system by its surroundings. A state becomes real and objective to us only when information about it has been so thoroughly and redundantly copied into the environment that it becomes impossible for any observer to not find it. The system has broadcast its state, and the environment has acted as a colossal amplifying antenna, ensuring that one specific broadcast, the one corresponding to the pointer state, is receivable, loud and clear across the entire universe, drowning out all the other faint quantum whispers. The survival of the fittest information leads directly to a shared common reality. This is the climax of our story, the resolution to the schism that has haunted physics for a century. The quantum world doesn't mysteriously become the classical world upon measurement. It is always in the process of becoming constantly imprinting its most stable information onto its surroundings. We simply come along and read the public record. This framework is so elegant, so complete, that it feels like the final chapter. But in science, a beautiful idea is not enough. It must be tested. It must make predictions that can be verified in the unforgiving crucible of the laboratory. If quantum Darwinism is true, if the environment is truly flooded with these redundant informational copies, then we should, in principle, be able to catch them. We should be able to intercept these tiny spies and read their messages. This quest to experimentally verify the central tenet of quantum Darwinism represents one of the most difficult and exciting frontiers in all of physics. It is an attempt to eavesdrop on the universe as it constructs reality to catch the act of creation in progress. For decades, this was considered a purely theoretical exercise, a philosopher's dream. The spies, the individual photons and phonons, are so numerous, so fleeting, and carry such a tiny fragment of information that detecting a statistically significant number of them seemed impossible. It was like trying to prove it's raining by catching a specific pre-selected set of 1,000 individual raindrops in a hurricane. But technology has begun to catch up with theory. Around the world, in hyper-sterile cleanrooms and deep underground labs shielded from cosmic rays, physicists are building exquisitely sensitive quantum systems designed to do exactly this. They are becoming detectives hunting for informational fingerprints left behind in the environment. One of the most promising approaches involves a tiny defect in a diamond, a flaw known as a nitrogen vacancy center. Here, a nitrogen atom and an empty space take the place of two carbon atoms in the diamond's perfect crystal lattice. This tiny imperfection behaves like a single controllable quantum system, a quantum bit or qubit that is exceptionally well isolated, yet can be precisely manipulated with lasers and magnetic fields. It is the perfect laboratory for studying the birth of the classical world in a controlled setting. In these experiments, scientists prepare the nitrogen vacancy center in a delicate quantum superposition. They then carefully couple it to a small engineered environment, often the nuclear spins of nearby carbon atoms within the diamond lattice itself. These carbon nuclei play the role of the spies. They interact with the central qubit, and in doing so they become entangled with it, each one carrying away a tiny fragment of information about the qubit's state. The challenge then is to develop the tools to read the state of these individual environmental spies' times without times disturbing the central system too much. It is a task of almost unimaginable delicacy. Using complex sequences of microwave pulses and laser bursts, teams of researchers can effectively interrogate these carbon nuclei one by one. They are asking each spy, "What did you see? What information are you carrying?" The predictions of quantum Darwinism are incredibly precise. As more and more of the environmental spies are measured, a clear pattern should emerge. Initially, when only one or two spies are interrogated, the information they carry will still be quantum and complex, reflecting the initial superposition. It's a jumbled, confusing picture, but as the scientists read out the third spy, the fourth, the 10th, the information about the superposition, the alive and dead part of the message should rapidly fade away. It is shared among all the spies in a fragile, holistic way, and looking at any small fraction of them isn't enough to reconstruct it. In stark contrast, the information about the stable pointer states the alive or dead part is copied classically and redundantly onto each and every spy. This classical information should plateau. After interrogating just a small fraction of the environment, say 10%, you will have learned essentially everything there is to know about the system's final classical state. Interrogating the remaining 90% will tell you nothing new. It will just confirm again and again and again the same fact. This predicted pattern, a rapid decay of quantum information, and a stable, redundant plateau of classical information is the unique, verifiable fingerprint of quantum Darwinism. And in recent years, multiple experiments from these diamond systems to those using superconducting circuits and photons have begun to see tantalizing evidence of this exact signature. They have watched in real time as information about a quantum system proliferates through its environment. They have seen the initial quantum secrets decay into nothingness, while a single robust classical fact is copied multiple times, creating a chorus of informational echoes that all sing the same song. These are the first snapshots ever taken of objectivity being born. We are learning to read the universe's private journal. We are developing the technology to trace the lineage of a fact from its uncertain birth as a quantum potential to its coronation as a shared classical reality. This experimental pursuit is more than just a confirmation of a clever theory. It is pushing at the very boundaries of what we consider to be measurement, observation, and reality itself. By learning to control and read out the fragments of information scattered into the environment, we are blurring the line between the system and the observer. In these experiments, the environment is also part of the measurement apparatus. The distinction begins to dissolve. We are discovering that the emergence of the classical world is not a singular, instantaneous event that happens when a conscious observer looks. It is a gradual, democratic process, a negotiation between a system and its surroundings. It is a story written piece by piece, word by word, by 1 billion tiny authors, and it happens continuously all around us whether we are looking or not. The universe is its own observer, its own memory, constantly recording the state of its most stable components in the most abundant medium it has itself. The implications of this are staggering, forcing us to ask questions that were once the sole domain of philosophy. If our shared reality is nothing more than a highly redundant database, a consensus reached through cosmic peer review, what does that say about the fundamental nature of the universe? We have long thought of the cosmos as a machine of particles and forces governed by immutable laws, but quantum Darwinism suggests a different picture. It paints a universe that is at its most fundamental level an information processing system, a universe where the primary currency is not energy or matter, but information itself. The laws of physics in this view are the algorithms that govern how this information is created, shared, copied, and perceived. The story of the cosmos is not just the story of exploding stars and colliding galaxies. It is the story of information struggling to survive, to become real, to be known. And as we stand here at the culmination of this grand synthesis, a new, even more profound set of questions begins to bloom in the darkness. We have found the mechanism that builds our classical world, the bridge across the quantum divide. But what lies on the other side of that bridge in realms where this mechanism might not operate? What happens in the empty void between galaxies where a quantum system might exist for eons without its information being redundantly copied by a dense environment? Does it remain forever in its ghostly state of potential? What happens inside a black hole where information is thought to be trapped, unable to proliferate and create an objective reality for those on the outside? Does quantum Darwinism hold the key to understanding these ultimate cosmic mysteries? By discovering how reality is constructed here on Earth, we may have inadvertently found the blueprint for understanding existence. Everywhere, from the heart of an atom to the edge of the visible universe, the architect has finally shown us the plans. Now we must dare to explore the rest of the magnificent, terrifying structure he has built. And so we arrive at the threshold, looking back from the solid ground of our classical world into the shimmering, uncertain haze from which we came. Our journey has taken us through the very heart of physics' greatest paradox, a chasm that for a century seemed impossibly wide, separating the ghostly realm of the quantum from the definite, tangible reality of our everyday lives. We have walked the echoing halls of superposition, where particles exist in a state of pure, whispered potential, being everywhere and nowhere all at once. We have confronted the jarring collapse of the wave function, that abrupt and mysterious moment when possibility crystallizes into fact, a process that long seemed to require the magical intervention of a conscious observer, placing humanity at the very center of creation. We saw how the cold, calculating touch of decoherence began to build a bridge across this divide, as the relentless chatter of the environment untangled delicate quantum states, forcing them to shed their ghostly superpositions. It was a monumental step, explaining why we never witness a cat that is both alive and dead. Yet even this powerful idea left us with a final haunting question. Decoherence showed us why possibilities narrow down, but it never explained why we and everyone else in the universe consistently agree on the single times outcome that remains. The world it painted was one of private realities, a multiverse of fractured perspectives with no guarantee of a shared objective truth. The puzzle, it seemed, was still missing its most crucial piece. That missing piece, we have discovered, is not some new exotic force or undiscovered particle, but rather an idea of profound and startling elegance, an idea borrowed from the very logic of life itself, quantum Darwinism. It enters the scene not as a revolution that tears down the old structure, but as a quiet revelation that illuminates the entire edifice, showing us how the familiar world is not a contradiction of the quantum, but its inevitable logical descendant. It provides the mechanism for consensus. It explains how the universe on its own, without any need for a conscious witness, performs a ceaseless and rigorous audit of itself, ensuring that all its inhabitants are reading from the same page of reality's grand ledger. The theory transforms the environment from a simple, disruptive source of noise into the central protagonist in the story of creation. It is no longer a clumsy vandal destroying quantum information. It is a meticulous, tireless press, taking the fragile, singular quantum state of a system and printing countless copies of its most durable information into the surrounding world. This is not a battle of existence, but a competition for posterity. It is a natural selection not of organisms, but of information itself. Think of a quantum system, an electron, a dust grain, a fledgling planet existing in its delicate superposition of possible states. Each of these potential realities reaches out and touches the vast environment around it, the photons of light bouncing off it, the air molecules colliding with it, the gravitational fields pulling on it. Each interaction is a whisper, a tiny imprint left upon a fragment of the cosmos. Quantum Darwinism proposes that only certain states, the so-called pointer states, are robust enough to survive this relentless interrogation. They are the states that can successfully transfer their information, their signature, into countless independent pieces of the environment without being destroyed in the process. They are informationally fertile. A state describing a planet in a definite location can imprint that location onto billions upon billions of photons, which then scatter across the galaxy, each one carrying a faithful, redundant copy of that single fact the planet is. Asterisk here, asterisk. A state describing the planet in a superposition of multiple locations is, by contrast, profoundly fragile. Its complex, delicate phase relationships are scrambled by even the slightest interaction, its information smeared into an indecipherable, useless mess across the environment. It fails to reproduce. It leaves no legible offspring. In this cosmic struggle for informational immortality, a clear winner emerges. The state that most successfully and prolifically disseminates its information becomes the consensus reality. The environment in its entirety conducts a vote. Every photon, every stray particle, every gravitational ripple becomes a ballot cast in favor of a particular classical truth. When you look at the moon in the night sky, you are not collapsing its wave function with the power of your consciousness. You are merely intercepting a tiny fraction of the ballots that have already been cast, a minuscule sample of the quadrillions of photons that have already interacted with the moon and are carrying the overwhelming agreed upon consensus. The moon is precisely times their asterisk. Your observation is not the act of creation. It is the final trivial act of reading the election results long after the polls have closed. We are not creating the world by looking at it. We are simply tapping into the universe's own colossal self-generated information stream. Objectivity, that bedrock of all science and philosophy, is therefore not some fundamental pre-existing quality of the universe. It is an emergent property born from the sheer overwhelming statistical weight of informational redundancy. The world appears solid and real and independent of us because the environment has already shouted its nature into existence, and our own senses are merely catching the final echoes of that deafening roar. This shift in perspective is nothing short of profound, fundamentally altering our relationship with the universe and our place within it. For centuries, we have seen ourselves as detached observers peering into a separate objective reality, as if through a pane of glass. Quantum mechanics shattered that glass, suggesting the observer was somehow inextricably linked with the observed. But quantum Darwinism rebuilds the window with a far more intricate and beautiful design. It reveals that observation is not a special privileged act reserved for conscious beings. Observation is happening constantly everywhere at every moment. A rock observes the planet it rests upon through the ceaseless exchange of gravitational and electromagnetic information. A cloud of interstellar gas observes the light of a distant star by absorbing and re-emitting its photons. We, with our complex brains and curious minds, are simply a highly evolved and incredibly sophisticated subset of the environment. We are a part of the grand cosmic mechanism of observation, not its prime mover. This realization is both humbling and empowering. It removes humanity from the mystical center of quantum mechanics, placing us back into the natural order of things as physical systems interacting with other physical systems. The universe doesn't need us to become real. The relentless democratic process of environmental monitoring ensures that reality will crystallize with or without a sentient mind to appreciate it. The implications of this idea ripple outwards, reaching from the smallest scales to the very largest. It offers a powerful new lens through which to view some of the most stubborn mysteries in cosmology. Consider the enigma of black holes, those gravitational monoliths that were once thought to be the universe's ultimate information destroyers. The infamous information paradox asks what happens to the quantum information of the matter that falls into one. Does it simply vanish from reality, violating the most fundamental laws of physics? Quantum Darwinism suggests a tantalizing escape route. Perhaps the information is never truly lost. Perhaps as the black hole evaporates over eons through Hawking radiation, the information about its contents is redundantly and robustly encoded into the outgoing photons and particles. The black hole itself becomes a part of the environment, imprinting a record of its history onto its emissions. The information survives not as a single fragile message, but as a massively duplicated, resilient archive scattered throughout the cosmos, waiting for a sufficiently advanced observer to piece it together. This theory provides a physical mechanism for how nature might preserve its own memory, even in the face of the most extreme objects it can create. Now cast your gaze back even further to the dawn of time itself. We look out into the cosmos and see the cosmic microwave background, the faint afterglow of the Big Bang. For decades we have studied its subtle temperature fluctuations, understanding them as the seeds of all cosmic structure, the primordial blueprint from which every galaxy, star and planet would eventually form. But what are we truly seeing? Quantum Darwinism offers a breathtaking interpretation. In the searing, dense plasma of the early universe, everything was an untamed quantum blur. But as the universe expanded and cooled, photons decoupled from matter flooding the cosmos. These photons, the very ones we detect today, acted as a vast primordial environment. They interacted with the quantum fluctuations of matter and energy, relentlessly measuring them. What we see in the sky today as the CMB is therefore not just a baby picture of the universe. It is the universe's first and most comprehensive self-portrait. It is a fossilized record of the moment the quantum possibilities of the infant cosmos were forced through a colossal act of environmental selection to choose a single classical reality. The patterns we see are the triumphant pointer states that survived this first fiery test, their information duplicated across a celestial sphere of photons for us to witness 13.8 billion years later. The quantum has become cosmic, its transition mediated by the very light that now illuminates our understanding. The journey, however, is far from over. Quantum Darwinism is not an endpoint, but a grand gateway to an entirely new landscape of inquiry. It reframes our most fundamental questions. By placing the flow and preservation of information at the very heart of reality's emergence, it suggests that information may be more fundamental than we ever imagined, perhaps even more so than matter or energy. Physicists and philosophers are now wrestling with this very idea. Is the universe at its core not made of particles but of bits? Is physical law simply the algorithm that governs the processing of this cosmic information? This is the frontier. Researchers are now designing experiments to directly test the theory, to catch the environment in the act of sifting through quantum possibilities and creating redundant records. They are trying to count the informational offspring of a quantum state, to quantify its fitness, and watch Darwinian selection unfold in the laboratory. Furthermore, the theory provides a crucial conceptual framework for our most ambitious technological dreams. The quest to build a functional quantum computer is in essence a battle times against time's quantum Darwinism. It is a struggle to isolate a fragile quantum system from its environment, to shield it from the relentless pressure to become classical, so that we can exploit the immense computational power of its superposition. Understanding the enemy is the first step to defeating it. And what of the final mystery, the mystery of ourselves? If a rock and a cloud can be considered observers, what then is consciousness? Quantum Darwinism suggests a possible, though still speculative, path. Perhaps a conscious mind is simply the ultimate expression of this universal process. It is a system so exquisitely organized that it doesn't just participate in the environmental consensus. It actively seeks out, gathers processes, and builds internal models of that information. A conscious being may be an island of hyper-efficient information processing in the great environmental sea. We are not magicians who conjure reality, but we are its most dedicated and sophisticated students. Our brains are biological instruments honed by biological evolution to excel at the very thing the universe has been doing since the Big Bang, gathering redundant information from the environment to build a stable, predictive model of the classical world. It connects the evolution of life with the evolution of reality itself, two grand Darwinian processes unfolding in perfect parallel, one of information, the other of flesh. The drive to know, to understand, to be aware, might be the deepest, most complex manifestation of the universe's fundamental drive to observe itself into being. So the next time you look up at the silent, star-strewn canvas of the night sky, see it for what it truly is. You are not looking at a static, finished painting, a reality that has existed for all time, waiting patiently for you to notice. You are witnessing the result of an ongoing dynamic and breathtakingly creative process that has been unfolding for billions of years. You are seeing a universe that has fought its way out of the fog of infinite possibility, its reality forged and tempered in the crucible of countless trillions of interactions. The light from that distant galaxy did not simply travel in a straight line to your eye. It was tested and confirmed at every step of its journey, its existence imprinted upon every particle of dust and every gravitational wave it passed. Its message of "I am here" copied and broadcast over and over again. Your gaze is but the final link in an ancient and unbroken chain of observation that stretches back to the dawn of time. We are not strangers in a strange land. We are the children of this process. We are built of the very atoms whose reality was cemented by this cosmic consensus. We are the universe's way of turning back on itself, of not only becoming, but of knowing that it has become. And in that knowledge, in that single shared objective reality born from a quantum storm, lies the deepest and most beautiful truth of all. We are all of us simply the cosmos awake.